So I'm going to make a short series of videos, and a series of short videos on the number theory for RSA. So we'll start with Fermat's little theorem, which says that if p is prime and a is any number, then a to the p minus 1 is congruent to 1 mod p. So we'll prove that in a second. Let's look at a picture of Pierre de Fermat. So this guy was a French lawyer, but he was responsible for tons of math, and he is most famous for Fermat's last theorem, which took something like 300 years to prove, 200 and something years to prove. And he's also famous for never giving or rarely giving satisfactory proofs of the truth that he discovered, including Fermat's little theorem. So I'm going to give a proof of this, but maybe before we prove it, we can just play around with it a little bit. So for example, this is saying that if suppose p is equal to 7 and a is equal to 3 or something, then this is saying that 3 to the 6th power, whatever that is, should be congruent to 1 mod 7. All right, so we have the ability to use computers to do these exponents, but let's do this one by hand just for a second. So we know that 3 cubed is congruent to 27, and so mod 7, that's minus 1 because 7 goes evenly into 28. Okay, so then 3 to the 6th power is 3 cubed squared, so this is the same thing as minus 1 squared then, mod 7, which is congruent to 1, and so it's true. And let's do the same thing now using the computer. So I've got an IPython notebook session open here. So what's your favorite prime? We can let p be equal to 37, that's prime, right? And let's let a be equal to, I'm just making something up, 11. Then what is a to the p minus 1 mod p? Let's see. Well, by goodness, it's 1, and this L here, I'm sorry about that, that's just saying that it's type long. So maybe this would be better. Yeah, so it's always true. And in fact, it's rarely true when p is not prime. So it's not an if and only if statement. So it's not the case that if p is composite, let's say that p is equal to 38. So is it the case that that every a that this will fail for every a? We'll find that it fails for some a, and it succeeds for other a. So we might find some a for which it succeeds, and so if I were, if I had done this beforehand, I could have already found one. But let's just use the Python set builder notation. What do they call this? They call this a list comprehension. So we'll do a in range from 1 to p. Okay, so those are the numbers from 1 up to 37. If a to the p minus 1 mod p is equal to 1. Okay, and then I have invalid syntax, of course. There should be a 4 here. So a for a, n, there you go. Okay. Oh wow. So for 38, this fails pretty bad. Let's try another composite number. Like I'm just making one up. 54. So by the way, maybe we should say just a little bit more about this. So this is saying that the only value between 0 and 37 for which the statement of Fermat's theorem is true is 1. Of course, it's always true for 1 because 1 to any power is 1. So that's kind of interesting. Let's try 54. Oh, and for 54, there are no examples of any. These things are called Fermat liars. So if this number is composite and you find an a such that a to the p minus 1 is congruent to 1, it's sometimes called a Fermat liar. Let me just write that down. It's going to be important later when we talk about primality testing. So a Fermat liar mod n is a number a such that a to the n minus 1 is congruent to 1 mod n. Okay, and we're going to use the computer to find one. We just have to try a few more values of p here. Let's go to 5. So I had to sort of bring out the big guns here. This number 561 is a known example where where there are many Fermat liars. In fact, everything in the multiplicative group mod 561 is a Fermat liar, and the numbers for which that is true are called Carmichael numbers. Let me write that down here. Carmichael number. So that is an integer n such that a to the n minus 1 is congruent to 1 for, mod n, for all a in the multiplicative group mod n. Okay, so there are such numbers. 561 is one. There's a Wikipedia article on these things, and you can research them further if you want to. Okay, so let's should we give the proof of Fermat's little theorem? This is going to be kind of boring and not super essential, so I will not be offended if you want to fast forward through this part. On the other hand, you might enjoy it if you're a masochist. So what is the proof of Fermat's little theorem? Proof. So to understand the proof, first you have to observe a fact, which is, let's just enumerate z mod p here. So z mod p is equal to, or how about z mod p star? So p is prime, so we've said in class that the multiplicative group mod p is just 1 to, so it's all the things that are relatively prime to p, but p is prime, so everything is relatively prime to p up to p minus 1. All right, and so we let a be any integer, but since any integer is congruent to any non-zero integer. Oh, by the way, is this a lie if a is 0? So yeah. So I'm assuming that a is not equal to 0. So let a be some integer which is not congruent to 0 mod p. Then consider the set a times 1, comma a times 2, comma a times 3, up to a times p minus 1. All right, and so this, you could think of this as the multiples of a mod p. Okay, and an amazing thing is true, which is this is just the original set. So in other words, the multiples of a are just the set itself. And so why is that true? It's because if so the only way that it could fail is if there are some numbers r and s such that a times r is congruent to a times s for r and s in zp star. So if that's true, then you can just multiply both sides by A inverse. So sorry, this congruence is mod P, of course. So if this is true mod P, then you can multiply both sides by A inverse, which exists because everything is relatively prime to P. So that means that the GCD of A and P is 1, and therefore A has an inverse. So if this is true, then it would be the case that R is congruent to S. Okay, so in other words, this set is the same size as that set, and it's also a subset, therefore it's the same set. Great. So what can you do with that? So now let's multiply all of these things together. So if we do A times 1 times A times 2 times A times 3 times A times P minus 1, this is going to be the same thing as 1 times 2 times 3 times P minus 1. Congruent, mod P. Why is that true? That is true because this is just the same set of numbers that you're multiplying because of this fact that we talked about earlier. So they have to be equal because this is just some kind of permutation of the same values that occur over there. So look at what's happening with the A's. Let's just collect all the A's. There are P minus 1 numbers, so there are P minus 1 A's. So on the left side here you have A to the P minus 1, and then what's left is 1 times 2 times 3. So we can just call that P minus 1 factorial. And on the right hand side you have P minus 1 factorial mod P. Okay. But since we're working mod P, this has an inverse because every non-zero number has an inverse mod P. And so we multiply both sides by the inverse of P minus 1 factorial, and what do you get? You get the statement A to the P minus 1 is congruent to 1 mod P. And so that is the proof of Fermat's little theorem. And you can stop watching the video now, but I think I'll go on to sort of play around with the notebook to sort of bore the hell out of anybody who's still watching. I mean, to confirm the truth of the things that I just said numerically. So let's look at, how about we look at just the product. Man, can we define product? Prod equals lambda x. Oh, yeah. Is that right? The product of a set. It's stupid. But I think I do have to do this, unfortunately. Why do I try to spell lambda like that? Lambda, lambda, lambda. Can I help you, help you, help you? So we'll take a list L, and this will just be, is there reduce? L, man, sorry, I'm going to pause the video and figure this out. Okay, and I'm back. And so I define this function product. So it's just the product of everything in a list. So the product of 1, 2, 3 is 6. So you can use this as just like a factorial function. So let's look at, how about the product of everything in the range of 17? Z17 stars is what I want. So these are the numbers from 1 to 16. And we'll do that mod, well, maybe we should just look at what the things are. So what is that? Okay. All right, so let me define this this other set, which is, let's just say A is equal to, what is A? A is 15, that's fine. So we'll do A times I for I in range from 1 to 17. And we'll put in mod 17 here. Okay. Okay, so notice that this just permutes this just is a permutation of the things in the range from 1 to 17. So if I just look at I mod 17 for I in Z17 star, it's just the same things permuted. So this is the fact that I was talking about in this part of the proof where we claimed that these two sets are the same. And so their product is going to be the same. So if I do the product here of this set, of course it's going to be equal to the product of this set. Right. And so yeah. All right. So that's all that I wanted to do, is just numerically confirm these claims. And so I think we've said enough about Fermat's little theorem. I'm going to stop.